So today we're going to talk about gravity, and we're going to talk a little bit more in depth about forces. So we're going to explain the effects that forces can have on objects and their velocity. We're going to be able to describe the force of gravity, and we're going to be able to define what terminal velocity is. So to begin, let's talk a little bit about forces. We briefly discussed that forces are pushes or pulls on objects. So, things like hitting a baseball with a baseball bat, or pulling a door open. All of those are forces, right? When forces on an object are balanced, one of two things happens, okay? If that object was already not moving and the forces on it are balanced, then that object won't move. So a box sitting on a table has the force of gravity pushing down on it and the force of the table pushing up on it. So forces on this box are balanced and it's not moving. If, however, the object is already moving and the forces on it are balanced, then it's going to move at a constant speed. Okay, so imagine your vehicle. You're driving on the road in this very, very cool car. Okay, your motor is pushing forward on the car, and the force of friction from the road is pushing backwards on the car. And when those forces are balanced, then your car moves at a constant speed, meaning it doesn't accelerate, it doesn't speed up, it doesn't slow down, doesn't change direction. Okay? Now, if you push down on the accelerator pedal and you make this one much stronger, then you'll speed up. And if you hit the brakes and add additional backwards forces, slowing you down, then the vehicle will slow. But if the force of the motor and the force of friction from the road are equal, then you travel at a constant speed. When forces on an object are not balanced, objects accelerate, like we just discussed with the car. If the forces aren't balanced, if one of them is stronger than the other, then that object will speed up, slow down, or sometimes change direction. Oh. Okay. Now, we've talked about forces, but mostly we've talked about very visible and easy to see forces. But not all forces that exist in the world are super easy to see, okay? We have some forces, which we call contact forces, that we can easily see. Contact forces involve two objects touching. So when you hit a ball with a bat, you see the bat hit the ball and push it forward. Okay? When two surfaces are rubbing past each other, you can see that one surface is touching the other. That is a contact force. Okay, for once in science, they named things in a way that makes it easier to remember. Contact forces, the surfaces are in contact. Okay? However, there are some non-contact forces, and these are forces where the objects don't touch. Okay? And they're difficult to explain. The science concepts about how they work isn't something we're going to cover in this science class, but all you need to understand about non-contact forces is that the two objects that are interacting don't actually have to touch for a contact force to be applied. Contact forces are things like gravity and static electricity. Okay? Those are attractive forces that exist, but the objects don't have to touch. So I can throw a ball up in the air and it will be affected by the gravity of Earth, even though the Earth and the ball are not touching. Now, there is one thing that I want to point out is a lot of people think that air resistance is a non-contact force because they can't see the air, but that doesn't make it a non-contact force. Non-contact means the objects don't touch, but if you swing your arm through the air, you can feel the particles touch your arm, right? So that is a contact force because the air is actually in contact with the arm or the ball or whatever thing it's working on. So while you can't see air resistance, not being able to see something doesn't necessarily make it a non-contact force. The only thing that makes it non-contact is the objects don't have to touch. All right, so now that we know what a non-contact force is, we can talk about gravity, okay? Because gravity is the most common non-contact force that we interact with, and it's the one that is especially important to our understanding of flight, which is what this chapter is about. Okay? Gravity is the force of attraction between any two objects. Okay, now, oftentimes when I would teach the idea of gravity to my fourth graders, the biggest surprise for them would be that there can be gravity between objects that does not include the Earth. Okay? Because here on Earth, our everyday experience, right, is that gravity is caused by the Earth. Okay? And for us here on Earth, that is the main force of gravity because the Earth is gigantic, which means its gravity is very strong, and it overcomes any other gravity we might be experiencing. Okay? But I want you to understand that if we removed the Earth from the equation, there would be a force of gravity between any two objects. Okay, so if Alex and I were floating out in outer space where there was nothing else around us, there would be a force of attraction of gravity between Alex and I because we are two objects and any two objects can experience that. But here on Earth, the force of Earth's gravity between us and the Earth is so much greater than any other gravity that it pretty much just ignores all other gravities and only focuses on the Earth's gravity. So as we talk about it in class, we're going to be talking mostly about gravity between objects and the Earth. On Earth, gravity causes any object that you throw up into the air to return back down to the Earth's surface. Gravity causes acceleration. Now, yesterday you guys calculated acceleration, and one of your groups was slightly under the acceleration due to gravity, and one of you was slightly over, which I really did anticipate to happen because it's very hard to time super accurately the time it takes that object to drop, okay? But when objects fall, they accelerate at 9.81 meters per second squared. So what that means is that every second that an object is falling, its speed increases by 9.81 meters per second. So the first second, it would be going 9.81, and then the second second, that would double, and then you would add another 9.81, and so on and so on and so on. Okay? But objects don't accelerate forever. They can only continue to accelerate until they reach what we call terminal velocity. And terminal velocity is different for every object that falls, okay? But terminal velocity is the speed at which the force of gravity downward is balanced by the upward force of air resistance, and the speed no longer increases. Now, that does not mean, as some people might think in their brain, that we stop moving. It just means the forces become balanced. Think back to that example of the car on the highway with the balanced forces, right? The force forward balances the force backwards, and they go at a constant speed. When you're falling and all of the air resistance pushing up on you matches the force of gravity down on you, you reach terminal velocity and you stop speeding up. Okay? When you jump out of an airplane with a parachute, the reason for the parachute is to increase air resistance so that terminal velocity becomes one at which you can survive hitting the ground. Okay? So the goal isn't to stop you in the air. The goal is to slow you down so much that by the time you reach the ground, you won't incur damage from hitting it at that speed. Fun and fascinating fact, squirrels' bodies are designed to handle the force of their terminal velocity. So a squirrel falling at its terminal velocity and striking the ground can survive that force, which is why you will see squirrels jump and leap out of very tall objects, because they are not going to incur injury when they hit the ground. All right, this is the end of our notes for today, and your homework is page 714, questions 1 through 4.